So first of all, hi everybody, and thank you to Lindsay and Eric for helping me to navigate how to get here and provide the presentation, etc. So I'm really humbled to be able to do this presentation today. It's been a long journey in my mind in less than 2 years from I didn't even know what AI was in the sense of an aircraft and what it meant. And then I got introduced to it and I met people like Ian and other people in the committee, which I'm now the secretary of the SAE G34. So what I want to try and do is give some insight, do a quick presentation with bullet points, and I'll talk around the bullet points and try and highlight what I've learned and where I feel things are going and what we need to do to try and convince ourselves that by putting this ML model, stroke enabler, stroke product on an aircraft, which is the most difficult aspect, because we can imagine we can do it on the ground. We can imagine we can do it in human resources and in the business sector. But when we want to put on a large aircraft, CS25, as EASA already knows, it's quite complicated, correct? So without further ado, I'll go into the first. So let's talk about machine learning. Well, for me, it has the potential to solve problems that traditional means cannot. And what I mean by that is, if you think about aircraft, they have problem statements. They have things that we could improve on beyond the baseline. There's always opportunities. And when we think about ML, it comes along and it provides an opportunity that maybe we should take it, because traditional software is not very good at the visual detection that a lot of people have talked about today. So we can see opportunities. We can see solving or improving beyond the baseline of safety, even environmental improvements, which are regularly discussed today. So ML in the end can have both a business sense. I work for Airbus, it's an OEM. It can make business sense for Airbus. It can make business sense for the buyers of Airbus products when they fly them for their customers. So it can have a selling point. And the selling point that I'll focus on today is safety, because there's an opportunity for safety to be improved, as I'll say, beyond the baseline. So we already have certified aircraft and they're ready flying today and they're safe. But can we improve on this? Can we go a little bit further? Can we take opportunities to relieve the stress that pilots have to face day in, day out, and our traffic controllers? So talking about our aircraft, the aircraft today are becoming more complex. I should know. I work in that arena and it is very tiring and complex. We're building system of systems. We're adapting the aircraft. We're doing modifications on top of modifications. We're doing derivative aircraft like the A321 XLR. It's a derivative aircraft, okay? We don't do clean sheet aircrafts anymore. They're very expensive. It's a long way before Airbus or even Boeing will start with a clean sheet aircraft. So it's all about adaptation. It's all about changing what you currently have, and you're adding functions on top of functions and complexity on top of complexity. And on top of that, the airspace is getting more congested. More aircraft are being sold. Thank you, Airbus is doing well, but that means they have to be flown and they're congesting the airspace. It's a big burden on our traffic control. It's a big burden on the operators. It's all about efficiency and understanding the routes and the complications of the density of the aircraft and the separation distance between aircraft. So one way of looking forward and trying improving is we need to link what I do now with traditional safety assessments. We have a way of doing safety. We have a process. It's defined. Existing ARPs dictate what we should do, and we follow that. And we follow the directions from the regulators, and we have our own internal processes. But what we do traditionally for safety is look at the development cycle. So we have the concept phase through the preliminary design review to the detailed design review to putting it in the ground testing to flight testing, permit to fly. When we put it out there and we end up putting it into service. And then when we put it into service, we sit back and look for feedback, which is called occurrence reporting. So there's a mechanism, part 21, which feeds back if there's misbehaviors or alerts going off in the cockpit and the crew reacting. So we get some feedback, but maybe we can tie the link between the traditional safety way of doing business on the design development and link it into the operational. So we talk about operational safety case. So a development and an operational safety case. And I believe that the game changer here is ML. I believe the opportunity for machine learning using sensors on the aircraft. We have an opportunity. Philip talked about it earlier. You know, he said about we have data analytics, but we have AI. And AI can change. We don't need to lean on the software so much in the sense of rule-based. We can now be data-driven algorithms. So there's an opportunity that should be utilized, in my opinion. So we can use ML to secure better operational oversight. At the end of the day, we're trying to have some sort of stewardship over flight operations. In a particular airliner, they have to safeguard their own fleet. They need to have insight of how their aircraft are behaving in the field, how their pilots are flying them, how the equipment are operating. Is equipment failing? Is it doing what it should do? Maybe we need to have a little bit more appreciation, and ML can provide that. But we have to use it wisely. And then we have to control its use functions. So this is the first thing that I want to talk about in blue highlight, of course, because it's about use functions. We talk about ML as being an enabler and it being a product. At the end of the day, it's an ML model, an algorithm, and it has to serve a function. It's an implementation choice. We need to understand that function. We need to make sure that that function is fit for purpose. It can do its job, okay? So it must do the job safely. Obviously, we'll talk about what happens if it fails or tells a lie. But first of all, we need to know the use function. And then secondly, we have to understand what I call reliance placed on that. This is when it goes wrong. This is when your ML tells a lie. And what I mean by lie is, it's where you have a ground truth, you have reality. And if you have reality, then the ML is trying to line up with reality. It's trying to give it an equivalence. But if it's far from reality, that's what's called a lie. And we'll talk about that later when I introduce the concept of confusion matrix. So reliance is what is essentially the safety effect or the credit. Guillaume mentioned about the bar being major. That is, in fact, a reliance. We're reliant that it doesn't go any higher than major for its sole failure or error or lie. How? Well, there's an AIR 6988 in 2019, which introduced a statement of concerns because it knew ahead of the game, just, you know, there's an ML product coming to town, an ML model. So what does that mean? What do we have to do about it? So then we came up with the ARP 6983 and the EUROCA ED 324. This is a standardization by consensus, by industry, with regulator participation, to try and ensure we have a development assurance process or to fill the development assurance gap. As Guillaume said, we follow what we currently do. We have a development assurance against software. We have a development assurance against complex hardware. Okay, so we're trying to provide some considerations with guidelines, with associated objectives against the ML model and how we need to cater for its uniqueness or specificities. Now, the coverage of industry scope is very wide and deep. If we think about, I think, somewhere in the region of 600 members. Now, who are the participants? Well, of course, Airbus are involved. There's Boeing, but we're not the only ones. There's Thales, there's NASA, okay? There's air traffic control players, ANS players. There's startup companies with their taxis, okay? So there's a lot of involvement. It's very widespread. And it's not just covering civilian, it's covering military. This standard, when hopefully after ballot next year, it gets implemented and introduced, will cover lots of the players in the aviation world. If you're an airship, it can cover you. If you're a space vehicle, yes. If you're military, yes. If you're civilian, of course, whether you're light aircraft or large aircraft, whether you're a helicopter. And what about the regulators? Well, thankfully, EASA is very heavily involved and very supportive and very useful with their concept paper to help us move along in the good direction. Of course, we also have the FAA. as a key regulator. And then we have ANAC in South America, Brazil, and then we have even the CAA of the UK. So we're being supported by the regulators, being involved and being interested and trying to help and secure a good standard that they can lean on when it gets published. So I'm now going to introduce my 3 themes, which is my holistic approach. So how do I break it down? How do I, as a signature, or how do I, when I'm in the SAE GD34 type thing, how does my brain work? I think about certification use reliance, or the acronym CURE. So we've talked about the use function. So that's your U. This is about the intent. In the large airplane CS25 1301A, it talks about be of a kind of design appropriate to the intended operation. What it means is your implementation choice. As said by Philip earlier, just choose ML because it's nice to do, and everybody will think, wow, that's sexy, have ML on the aircraft. We would only choose it because it's the wise thing to do. It's the appropriate implementation choice, i.e. it solves the problem statement, it has the selling point. Otherwise, we'll use software, thank you very much, or we'll use traditional hardware or complex hardware. So back to the ARP 6983 and the ED 324. Here, there is going to be obviously a standard document by consensus, which will provide guidelines, but uniquely, it will also provide associated objectives. And this is unique because if we think about RTCA 178C for software or DO 254 for complex hardware, they provide objectives. But the ARPs traditionally, 4754, do not provide explicit objectives. So we're changing, I say, the scene in having objectives to help the development assurance. Then we need to know, in part of the CURE, the reliance placed, as I've said. What is the credit taken? In safety, Baptiste mentioned it earlier, we do the functional hazard analysis. So the first thing we want to do is, okay, what is your function? Now, if we assume your function is going to work, then what happens if it fails? So what if it's lost, detected or undetected? What if it provides erroneous data, detected or undetected? So we need to do a functional hazard assessment. But now we're going to do it in an implementation choice that we're not really familiar with. And what does that mean? So someone like me who's an approver, I need to have an understanding of how the FHA is being conducted and whether it's acceptable. The regulator who's approving the modification would also need to know, they're interested of what are you trying to do here in your FHA? What are you trying to do in your what we call means of compliance 3 at the final SSA? So then we go back to the first letter of the acronym CURE, which is certification. So you need to secure regulator agreement on the high. Here was just Hugo, I think, put up about the CRE. So if we're working with the EASA, we may have to use the EASA concept paper and we'll have a certification review item. If we're working with the FAA to try and secure approval, then they want to lean on issue papers. So it's a case-by-case approach because they have not at the moment written their equivalent concept paper or their technical expectations. So back to it, the FAA is an issue paper approach, as I call it, case by case. If an applicant wants to get approval, they submit their means of compliance. They submit their case, like going in front of a judge. Submit your case. EASA is more formal. They have an EASA concept paper. And here it'll be per product or per function or per system. Then it would be follow the EASA concept paper, depending on your reliance. If the reliance is major, that can be more harsh than if the safety objective is minor. And then there is the ARP 6983, which we're working on, but is not implemented, as in it's not been published yet. And hopefully when that gets published, then that's another one. That's 3 choices, okay? So what we need to do is limit the risk by certification use reliance. That's the way I look at it. We need to understand that we need to certify or get approval of a product or its modification, which in this case uses an implementation choice of machine learning. We need to understand the function. What is it trying to do? What is its need? It's there for a need. I think the guy from Dassault said it very well. It's about the need. Does it serve the need? And then there's the reliance. What happens if it goes wrong? What happens if it tells a lie at the bad time on the flight? It can tell a lie a lot of times. That won't hurt you. It's when it lies at the very bad time, when you really need it. A pilot needs it to make a decision. And at that decision point, if the pilot has been told a lie, either the pilot follows it and believes it or overrides it, but still, it causes a confusion. So it needs to be fit for purpose. And as said by Hugo as well, it cannot generalize. He's seen something that can generalize to unseen data. This is what we wanted to do. We don't train it to all the data. We test it to unseen data after we think it's ready. When we put it out in the field, we're hoping that it will generalize to unseen data, i.e. the gap will not be too big. Okay, so we start low risk at use functions. We need to be incremental. We need to be cautious. And the bar, as set, is major sole risk. This is already explicit in the ARP, even if it's in draft. The bar is set at no higher than sole contribution of major. We're non-adaptive. It's learned off the aircraft. Okay, we don't learn on the aircraft. This is from the ARP. We restrict types at the moment in the ARP ED324 to supervised. Of course, next iteration after the first publication, we will go towards unsupervised or semi-supervised, and potentially we can go on to reinforcement learning. Although that I think is very far away, but certainly not for the military. ARP 69983 is the best means of product level of confidence. Because when we think about software, when we develop software and we qualify it, we're looking at a level of confidence. What does that come from? It comes from reviews, tests, inspections, and analysis. So when we're looking at our ML, which is another algorithm, we're going to look at the same reviews like preliminary design review, critical design review. We're going to look at inspection. Our analysis may be statistical because it's more a mathematical algorithm. So we're going to look at statistics. Treat data learning algorithm the same as the rule-based software, essentially. All hardware is treated the same as traditional means. Be careful of hardware susceptibility to data distortion. So here we need to look at the RTCA DO160G to see whether that itself is fit for purpose to cater for ML. But we need to make sure that we test, ensure that the hardware, like the sensors, and through the pre-processing, that we do not corrupt the data. I think the lady this morning, Isabel, explained that a very slight change can make a big difference. So data distortion is a threat we need to understand. It's not just about Kalman filters, guys. Skill shortage. So I'm a safety engineer and there's already a skill shortage of safety engineers. But I'm talking about safety engineers adapting to ML. And there is definitely a skill shortage in safety engineers knowing how to deal with ML. A very big gap. So we need to improve on that. We need to invest in training. I do training myself at Cranfield University, internal in Airbus, to try and help fill that gap. Safety FHA must drive specification requirements. So the functional hazard assessment must look at how to influence the specification, how to influence the development. And that comes from performance metrics as one means, because they're synonymous with safety. Performance metrics can be things like recall against your false negative or precision against your false positive rate. So we need to have an understanding of what we want to influence. Is my greatest threat a false negative, or is my greatest threat a false positive? Confusion matrix. This is where we break it down into four conditional states. So the ARP has guardrails. We need to ensure data set completeness, representative correctness. We need to understand the ML model, the type, hyperparameters, the parameters. We need to do scenario testing, and we have an ML constituent, which is the container, which holds the ML item. Secure the agreed reliance internally and with the authority, because that secures the development assurance and the objectives pertaining to that particular ML model. So 3 pillars of cure. So first of all, apply the 6983 ED324 for the level of confidence, performance metrics to agree minimal performance targets. And I say minimal because there has to be an acceptable level of performance against thresholds. Ensure fit for purpose in operation. Ensure the final software item is equivalent. So there's no regression or acceptable regression. When you translate it into a software item, you need to check that. And then, sorry, back, there was the monitoring and recordings, which is important. You need to monitor, you need to record data as necessary. So in conclusion, the technical advances of machine learning can and should be harvested for safety above the baseline. We can have opportunities to improve. We can seek improvements in our oversight of aircraft in operations, vitally important. Fill the gap, connect the dots in the operations. We have an opportunity. Think about ground taxi collisions. This is rising. Okay, we could imagine we can reduce those, which means less AOGs, being better aware of equipment failures as they happen in the air, so we can turn around the aircraft quicker. And we can spot anomalies in operations, i.e. misbehaviors, or in the same fleet, pilots are operating the aircraft differently. And we can therefore reduce unacceptable aircraft on grounds, which I'm sure our customers would love. Thank you very much.